we are finally moving into the last topic for the entire semester. So starting from today, we are going to deal with time-varying fields. This is Jen's textbook, chapter 7, right? Let us review what we have learned, what we have covered up to now. This is pretty much up to now the entire semester. In front of you, the 4 equations. Over to the left, these 2 are related to electric fields. And over to your right, these 2 equations are dealing with magnetic fields. But up to now, we only concerned static fields. Okay? So nothing is moving, and the fields are not changing against time. Right? And therefore, these 2 equations are regarded as the electrostatics, and these 2 are considered as magnetostatics. So everything is stationary, not moving. And also the field quantities, all these vector field quantities are only a function of space, but not of time. Okay? And it is due to this assumption. Everything remains static, not time varying. So up to now, the 4 equations can be considered independent from each other. Okay? Meaning that, if you still remember, in our assumption, in all the analysis, for electrics, we mentioned in this space, we only have electric field. We don't have magnetic field. And when we entered into magnetism, we assumed in this space, we only have magnetic field and no electric field. So these 2 boxes are viewed as independent, meaning they don't have any communication, right? And that is only true when you consider statics, right? So starting from today, we are going to deal with time-varying fields, meaning this E, D, H, and B, and even J can be a function of space and time. Okay? Let me just use a generalized vector expression. Okay? So all these vector quantities are now functions of space, 3-dimensional space, and time as well. So when we take time into consideration, then some of these postulates need to be modified. Okay? We have 4 postulates for statics. And now we're having time variations. So take a guess. How many equations, how many postulates need to be modified? If all 4 of them need to be modified, then we're not very happy. Okay? But in the end, only the 2 curl equations need to be modified. So the 2 divergence equations, this one and this one, do not need to be modified. Okay? So even though in the most generalized case, you have spatially dependent field and you also have time-dependent field, these 2 divergence postulates remains the same. Okay? So we're lucky. We only need to modify these 2 curl equations. Okay? And these 2 curl equations need to be modified to prevent violation of one experimental observation, which is later called Faraday's law. This is purely experimental. Okay? So seeing is believing. when you see this effect, you have to modify your equation. Okay? The second consideration is used to modify the curl of H, the Ampere's circuital law. Well, it's also partially due to experimental observation, but partially due to purely mathematical identity. Okay? So we will discuss this later in details, but up front, let me just tell you, we only need to modify these two curl relationships. Okay? So when we perform the modification, somehow, we have to modify these two curl equations. And then we find out, under time-varying fields, when these two curl relations are correctly modified, electric field and magnetic field, they actually communicate. They talk to each other. Okay? That's the meaning of coupling. They are coupled together. If this one is getting weaker, maybe this one is getting weaker as well. So they are somehow correlated. They're related. Okay? And that means when we have a time-varying field, they are all somehow related. So if we want to solve them, we cannot just solve one. In the past, in statics, we can just solve E field and without knowing the magnetic field. Or in magnetostatics, we can only solve for the magnetic field without needing to know the E field, right? That's our assumption. In this space, we only have one field. We don't have the other. But now the situation is different. When you have time-varying field, you have to know both simultaneously at the same time. Okay? So that's a major difference. So you have to solve them simultaneously because they are coupled. If you don't know one of them, you don't know the truth. Okay? So in the end, this is nothing to fear. As I promised you, how do we start this semester? We kicked off this course by introducing transmission line. And what do you have on transmission line? You have a traveling wave, right? In the form of a traveling voltage and a traveling current as a function of space and time. And the reason I organized this course in this way is you start from the total view, right? And you gradually increase your knowledge so that you know what the professor taught you up front is real. Okay? Initially, you were forced to accept my opinions, but now gradually you know those are all true. Eventually, when you have time-varying fields, you are solving for electromagnetic waves. Waves propagate. Okay? If you still remember, waves carry energy, they can propagate, so they are obviously functions of space and time. Okay? That's what we encountered in transmission lines. Right? So after the entire semester, after 13 weeks or so, you are now having the adequate knowledge to really understand what was covered in transmission line. So now we are dealing with electromagnetic waves. Right. So the PowerPoint set is organized to cover Faraday's law in details, and then we are going to derive for Maxwell's equations. In my personal opinion, the entire semester is only to prepare you to appreciate and understand Maxwell's equations. As you can see, equations, you have multiple equations, all right? In the end, there are a total of 4 equations. And if you understand these 4 equations, you know electromagnetics. So think about it. You only need to understand 4 equations to earn good grades in this course. But luckily, look at these 4 equations. Do you need to learn more equations? Maxwell's equations, how are they related to these 4 equations? They're actually the same. After you perform the correct modification to deal with time-varying fields, these 4 equations are called Maxwell's equations. Okay? So for the entire semester, you're learning just 4 equations. This is the easiest course to pass, right? And to get very high scores. And very shortly, I will talk about the boundary conditions when you have time-varying fields. Okay? Extremely simple, maybe just 2 slides. So today we're going to talk about Faraday's law in details. Okay? And we are going to talk about how Faraday modified the fundamental postulate. And then Faraday's law can be presented in 3 different scenarios. I'll talk about them later as we move. Okay, there's no meaning defining them now. So let's jump to the observation. So this is Michael Faraday. He grew up from a very poor family. So basically, he is a self-taught scientist. This is something you have to respect. Okay, he didn't really receive any formal education. So he performed one experiment. So he had a lot of wires winded. So you have coils. And somehow he inserted some magnet. Okay? By inserting the magnet or pulling the magnet out, he was able to see a lamp being bright or dim. Okay? If you have a lamp being bright, means you have current conducted over the lamp, right? So in a more fancy picture, you have a coil, right? The coil can have currents, but initially you're not providing any current. You don't have a current source. You don't have a battery. So ideally, over this coil, you don't expect to see any current, okay? Now, if you connect this coil to a voltmeter, which is having some resistor, if you have current flowing across it, you measure a voltage, right? A potential difference. So his experiment was, well, by inserting a magnet into the coil or out of the coil, he was able to see, well, you can produce voltage. So what does that mean? That means in a closed loop, this coil forms a closed circuitry, right? And you are not providing any additional source. You are not having a battery. At that time, people don't have batteries yet. So somehow magically, just by inserting and pulling out this magnet, he was able to see, well, the voltage or the current changes as a function of time. And that change corresponds to the movement of the magnet. So after more than 100 years, if you know this, if you perform this experiment, were you able to modify the equation? Although seeing is believing, but usually we see and we accept, but we don't dare or we are too lazy to modify the math because we're not very good at math. We're engineers. Okay? But this self-taught man was brave enough to say, from his observation, curl of E equals to 0 is not correct. Are you able to justify his statement? Why is this experiment, the result from this experiment is violating this postulate? So what's the physics behind it? What's the philosophy or physics behind the violation? Do you still remember what is being said with this equation? Curl of E is equal to 0 tells you E fields are conserved fields, right? And we use this fact to show Kirchhoff's voltage law is nothing more than this equation. So if you have a closed loop, you walk around this closed loop, you don't gain any voltage, right? You take a walk around this building, you don't grow taller, right? That's what this equation is telling you. So if that is true, you have a closed loop, and every point on that loop is not having a voltage source or a current source. How can you generate current, right? He is asking, where is this induced current coming from? You only have a closed loop. If you want to have a current, what do you have to have? J equals sigma E, right? We formed the closed loop by having the metallic wire. So the metallic wire is having some conductivity, but without any voltage source or current source, E is equal to 0 and J is equal to 0, so you don't expect to see any current. But by inserting that magnet or pulling the magnet out, he was able to sense or observe or measure current or voltage, and that strongly violates this equation, right? Out of nowhere, you can produce voltage in that non-driven closed circuitry, right? So he realized this must be changed when you have time-varying magnetic field. Why? By inserting this magnet, what is a magnet? A magnet produces magnetic field lines, right? When this magnet is very far away from this loop, how many field lines from the magnet would penetrate and go into this coil? Probably none, right? But as you move closer and closer and actually into this coil, then all the field lines created by this permanent magnet is forced to penetrate across the coil cross-section. And that movement creates a time-varying magnetic field across the section, the area, okay? So he was smart enough to say, this is not right. I should modify to this form. When you have a time-varying magnetic field, or the magnetic flux line, the number of magnetic field line is a function of time, right? When you insert and you pull out, the number of field line is therefore a function of time. And that change of magnetic field line is a source to create the observed current or voltage. So if you compare the two equations, you have the same curl of E on your left-hand side, but this one is having 0 on the right-hand side of the equality sign, but this one is having a non-zero. What does that mean? What does that mean? This equation is telling you curl of E is equal to 0, and therefore the E fields, as we stated, E fields are always conservative. But now suddenly Faraday is telling you, hey, curl of E does not need to be always 0. Under certain conditions, it can be non-zero. And that condition is you have to artificially provide a time-varying magnetic field. A time-varying magnetic field line number. Okay? So over this cross-section, you have to make sure the number of magnetic field line penetrating across this area is a function of time. Okay? So this is in differential form. In integral form, if you still remember, Kirchhoff's voltage law is using this one, so the closed loop integration of E dot dl is equal to 0. That's Kirchhoff's law, voltage law. But now, having this relation, this is telling you when you have a time-varying magnetic field and you do have a loop cross-section, you perform the calculation, you perform the integration. This is nothing more than just by knowing, evaluating how many field lines you have at certain time instance and how they change as a function of time. And then you have to take a negative sign, and that becomes your potential difference, right? If you still remember, E dot dl, making an integration, is trying to evaluate your potential difference. But this is over a closed loop. So in the past, when you don't have a time-varying magnetic field, you start from point A, right? If you have a closed loop, say this is A, B, C, D. You start from this point. So this is having VA, VB, VC, VD, right? You walk around, you come back. What is your potential difference? 0. And that means you're dealing with a conserved field. But now Faraday is saying it's not true anymore. If you have time-varying field, magnetic field, then you walk around a closed loop. You walk around once, you have VA1 prime. You walk around twice, you have V2, VA prime. And these are not equal. Right? So this is like magic. This means we start from the door of the classroom, we walk around this building, and you grow taller. Oh, that's magical. We can join an MBA, right? So what does that mean? This E, please do remember, this E or this E is something different from the E that we learned in the past. In the past, curl of E equals to 0 because we were dealing with static fields. Everything is not a function of time. So this E is a conserved electric field intensity. So now that we're dealing with a time-varying magnetic field, this E should have its own name, okay? So therefore, I'm calling this E with a subscript I. This is an impressed E field, okay? So let me just, using this subscript to differentiate from the past. This means whenever you have a time-varying magnetic field, that can create, that time-varying magnetic field can give rise to a new type of E field, which is totally different from what we have learned in the past. Okay? So why don't we call it using its own name? So now we take this equation. We take a look at this equation. What Faraday meant was the total E field is equal to the negative time variation of the magnetic field. So once you view E as the total E in the sense, then he connects the time varying part to the static part. Why? The total field can be decomposed into this old static part, conserved part, plus this impressed part. This is non-conserved, right? When you take the curl of these two, curl of E plus curl of EI, so curl of E still remains to be 0. It's static. So when you deal with static field, that remains to be true. But the E field can also have the AC part, right? This is the DC part, you're electrical engineers. DC part, AC part. AC part have to use this equation, right? So this is what he meant. What he really meant was he only wants to say that the E fields can be decomposed into the static DC part or the time-varying AC part.